Well, let's continue with our rules or laws of exponents. So suppose we have a to the m times a to the n. Well, that can be simplified. And how do we simplify that? I can write a just one time, and what would the exponent be? You add m to n. A to the m plus n. And if you forget that, come up with a very specific example. Say something like, I'll go way up here for an example. A squared times a to the third. Just write it out. A squared is a times a to the third, which would be a times a times a. You wrote two of them, and then you wrote three of them, and you're multiplying them all together. And that's a to the fifth power. And how did we get that exponent of 5 from the very beginning? Just added 2 and 3. Okay? This next one is a to the m, the whole thing raised to the nth power. Do you remember what that is? It's going to be a raised to what exponent? Well, you multiply the two exponents, m times n. So it's just a to the m n. And similarly, if you forgot that, just do an example. A squared in parentheses raised to the third power. Well, the parentheses are being raised to the third power, what's in the parentheses. So you need 3 copies of them. Oops. Sorry, that third a looks like a d. So a squared, a squared, a squared. And now we know that when you're multiplying 3 terms with exponents where all the bases are the same, a, and a, you can just add these. 2, 4, 6. It'd be a to the 6th. And if you forgot, again, you could write out each a squared as a times a, times a times a, times a times a, and there are 6 of them. So that's a to the 6th power. And how did we get a to the 6th from a squared to the third? We multiplied 2 times 3. All right, this last one's pretty easy. Not the last one, but the third one. If you take a product and you raise them to the nth power, ab in parentheses raised to the nth, you can raise each term to the nth power. So a to the n, b to the n. Okay, notice in each case we simplified, but basically it means we wrote it in a way where we, at least for these two, where we didn't need parentheses anymore. Here and here. All right, well now let's do the opposite of this one. Opposite, by that I mean instead of multiplying, we're now dividing. Fraction, it's a top divided by the bottom. How can we write that? It's going to be a to what exponent? Well, in this case, instead of adding, we subtract. The top exponent minus the bottom exponent, a to the m minus n. And you could do a real simple example. Let's say we had a to the third over a squared. Well, you could just write it like this. This is a to the third over a squared. A to the third has an exponent of 3. 3 minus 2 is 1, so we know this is equal to a. Maybe I'll do it here. A cubed over a squared, really small, is equal to AAA over AA, and then you cancel that one, you cancel that one, and it leaves you with one single a, which is a to the 1, and you could have done it just by saying 3 minus 2 gives you 1. Okay, the last one of these exponents is a fraction raised to an exponent. This is one we saw in a previous video. If you have a fraction raised to an exponent, you can take the numerator and raise it to the exponent over the denominator raised to the exponent. Now let's do some examples. Okay, well we have 2 terms here. They both have exponents and the base is the same, an x and an x. So what is x to the 4th times x to the negative 7? It is x to the 4 minus 7. You add the exponents. 4 plus a negative 7, 4 minus 7, x to the negative 3rd power. Now, I'm running out of room here, but how could I rewrite that? That's 1 over x to the positive 3. You could write it like this, or you could write it like this. Usually we prefer positive exponents. And you may be asked in homework problems to write it with positive exponents like that. Okay? Just remember, a negative exponent means you take the base and take the reciprocal of it and raise it to the positive value of that exponent. Okay, x to the negative 5th, all squared. In this case, we're going to multiply the two exponents together because you're taking x to the negative 5th in parentheses raised to another exponent. That's x to the negative 10, which could be written 1 over x to the 10th power. Actually, a better way to write it. Here we have two things multiplied together, 3 times z, both raised to the 3rd power, so that's 3 to the 3rd, z to the 3rd. And we know 3 to the 3rd is 27. We might as well simplify that. There we go. Okay, now we're going to use this, we call this the quotient rule up here. Remember where you take the top exponent and subtract the bottom exponent? So it's going to be w to the negative 3 minus negative 7. Don't forget, it's minus the negative 7. Don't just say negative 3 minus 7. So negative 3 plus 7 gives you 4. So that's w to the 4th power. 2/3 to the 4th. Well, that's 2 to the 4th over 3 to the 4th. And that's all. We could leave it that way, but since we know those answers, I think, 2 to the 4th looks like it's 16. 2 times 2 times 2 times 2. 3 times 3 is 9 times 3, and times another 3 gives you 27. 81. Okay. And this one didn't come out correctly in the printer. This should be raised to the 3rd power. So we have x squared times z. So we're going to take x squared to the 3rd times z to the 3rd. So x squared in parentheses to the 3rd, z to the 3rd. But that x squared to the 3rd is simply x to the 6th. Okay. All right, number 9. The principal square root of a positive number, or I should say non-negative, it could be 0 or greater. Principal square root is the non-negative number such that b squared equals a. And it's denoted like this. This is the principal square root of a. And we're setting it equal to b, but it is defined this way. If b squared is equal to a, then b is equal to radical a. Okay? And the reason we're calling it the principal square root instead of the square root is because, for example, if I said, what's a square root of 9, you would probably say 3. Now, the correct answer is 3 or negative 3. There are 2 square roots of 9. Negative 3 squared is 9, and 3 squared is 9. But when you say the principal square root, I just want the positive one. Okay, so radical 49 is 7. Even though the number 49 has 2 square roots, plus and minus 7, when you put the radical there, it means give me the principal square root, the positive version. And how about this? Well, radical 1/9, similar to exponents of a fraction, when you take a fraction and raise it to an exponent, we can take the radical and apply it to the numerator and the denominator. Radical 1 over radical 9. And how does that simplify? 1 over 3. Now here's one that I hope you don't think about too much. The square root of 2.3, I have no idea what that number is. I mean, I could guess closely, but I don't know exactly. But the point here is if you're taking the square root of a number and then squaring it, it takes you right back to where you started. And maybe a number like, maybe this would be easier to see as an example. I should get 4 right here. Because I'm taking the square root of it, the principal square root, which is 2. 2 squared is 4. So when you have a radical of a number and then square it, the squaring and the radical kind of cancel each other out. All right, let's solve a very simple equation. Let's solve for x. Okay, so the first thing I'm going to do is simplify everything first by using the distributive property right here. And this is where, if you're going to make a mistake, this is where you're probably going to make it. 2x. Negative 3 times x is minus 3x. Negative 3 times negative 4 gives you positive 12. That might be where some of you make a mistake. You forget to carry the multiply the negative sign through as well as the 3. Negative 3 times x, negative 3 times negative 4. So that's a positive x equals negative 17. I'm going to combine these two terms together to get 5x. I'm subtracting 3, so negative 1x. Negative x plus 12 is equal to negative 17. So we subtract 12 from both sides, and I'm going to go up here now. And I will get negative x, that cancels out, negative 17 and minus 12, so I can think of it as negative 17 and negative 12 would be a negative 29. So if negative x is negative 29, you multiply both sides by negative 1, and you get x equals 29. I'll let you plug that in yourself to verify that's the correct answer. So you do 2 times 29 minus 3 times 25, because that'd be 29 minus 4 would be 25, and you should get negative 17. All right, let's solve inequality now, an inequality. Here's where if you're going to make a mistake, you might make a mistake because you forget to do this note right here. If you multiply or divide both sides of an inequality by a negative number or something, a negative expression, anything that's negative, then what? Then you must reverse the inequality. So if it's a less than, you make it a greater than. If it's a greater than or equal, you make it a less than or equal. Okay, so let's do this. Let's solve this simple inequality. I want to get all the x's on the left side and all the numbers on the right. So I'm going to do a minus 3x on both sides. It'll keep negative 5 by itself on the right. Okay, so an x and negative 3x would give us a negative 2x plus 2 is equal to negative 5. And now I'm going to subtract 2. Oops, not equal. That's less than or equal. Okay, now I'm going to subtract 2 from both sides. We don't reverse anything here because we're not multiplying or dividing by a negative. We're just subtracting a number. We're subtracting 2. So negative 2x less or equal negative 5, negative 2, negative 7. And then finally, we divide both sides by negative 2, and here's where we have to do the swap, or reverse of the inequality. We divide it by a negative, and we get x greater than or equal to negative 7 over negative 2 is the same as 7 over 2. That's one way to write the solution, but we also said we solved for it and graph it on the real line. So draw a real line, and the only number you need to put on it is 7/2. And then we're going to shade everything to the right of 7/2, not the left. Everything greater than. If x is greater than this, it means it's to the right of 7/2. And you may remember, since it's greater than or equal, we used a solid circle, and we'll cover that in class at a later time as well. So we shade this. So here is the solution written one way, and then here is the solution written on the real line, just by shading the real line. Okay, that finishes our brief review of algebra.